So, welcome to today's Cycle 47R3 webinar. Andy Brown, Director of Research at ECMWF, will give an overview of the new IFS model cycle, which is scheduled for operational implementation in 1 month's time. My name is Carsten Maas from the User Outreach and Engagement at ECMWF. Before we start, just some organizational points. Please note that this webinar will be recorded and the recording will be made available from our 47R3 implementation page later. So please keep yourself muted during the presentation. There will be an opportunity to ask questions using your microphone after the presentation or at any time using the chat facility in BlueJeans. And with that, I give straight over to Andy.
Okay, thank you very much, Carsten, and good afternoon, everybody. It's a pleasure to be here. As Carsten said, I'm Andy Brown, Director of Research. So I shouldn't actually really be here at all. We do an upgrade to the IFS approximately once per year. And our original plan was we did cycle 47R1, and then we migrate to a new supercomputer in Bologna, and then we'd have cycle 48R1. A year or so ago, we decided to accelerate some of our work, so we introduced an extra cycle, 47R2, and that's where we introduced single precision to the forecast model and higher ensemble vertical resolution, and that was successfully implemented in May. And now, maybe getting greedy, we're bringing forward a second cycle for this year, 47R3. And at this point, I would really like to pay tribute to all the ECMWF staff involved. As I said, the usual rhythm is 1 cycle per year, and here we have 2 additional cycles within 5 months of each other at the same time as the supporting work for the migration to the new supercomputer, and that done at a time when, as everybody would understand, has been huge disruption with everybody working at home. So I think it's quite an achievement, and really thank you to all the ECMWF staff that have enabled this. I'll say more about the cycle contents in detail in the next few slides, but at the highest level, we've got changes to the observation usage. We've got the introduction of weak constraint 4D VAR for the stratosphere in the ensemble of data assimilations, and we've got a very, very major revision to the moist physics in the IFS. So just to sort of get into these in a bit more detail in terms of what's in the cycle. So the first change is the assimilation of AMSU-A, switching that to all sky. So at ECMWF, we've been on a very long journey, probably 10 or 15 years or so, of moving from using microwave satellite data just in clear sky conditions to also using it in all sky conditions. So when there's cloud, we're still using the microwave data. And we've previously done it with microwave imagers, and we've done it with humidity sounders. This is, if you like, the final step, the first use of the all-sky framework for the temperature sounders. So the AMSU-A channels, the clear sky assimilation replaced by all sky. And if you look at the figures, this is just a single case study example, but I think it's illustrative. So this is the case of Hurricane Humberto. The hurricane is actually inside the circle. And all the coloured dots on that panel are the observations minus background, where we currently operationally using this microwave data. And you can see there's a good coverage, but you see some gaps, some white spaces in that plot, and that's where we're not using the microwave data because of the clouds. And if you go to the panel to the right, that's the same thing in the all sky framework, and you see it's filled in the gaps, in particular in the area where the hurricane is. And I guess the good news story is, we'd hope that extra data would improve the quality of the forecasts. And the scatter plot on the right there is looking at using all sky AMSU-A on the x-axis, clear sky AMSU-A on the x-axis, and this is looking at the errors in the hurricane tracks. And you can see we're improving the hurricane tracks with this all sky approach, and we use a lot more data. The next changes in the data assimilation, improving the upper atmosphere. We've got new RT-TOV coefficients for the hyperspectral infrared sounders. So that's the radiative transfer scheme improvements, and that leads to the analysis in the background giving a better fit to radiosondes, and we get a small improvement in the forecast from that. And then the next change is the weak constraint 4D VAR in the ensemble of data assimilations in the stratosphere. This is something we introduced in cycle 47R1 to the high-res system, where the data assimilation is effectively learning a model error term, which it applies in its data assimilation cycling. That dramatically improved the high-res analysis stratosphere when we introduced it. This is making the corresponding change in the ensemble of data assimilations, and we see very major improvements in the stratosphere, as we'd expect. Then the last of the data assimilation changes to improve the wind analysis. There's two parts to this. The first one is atmospheric motion vector products. So one of the challenges with these products is deciding at what height the winds are. So tracking the clouds to get winds, but then you have to assign them to a certain height. And we looked at the original heights that comes with the tropics, and we're finding that comes with the product, and some of the sort of lower level atmospheric motion vectors in the tropics were really not matching our sort of model background very well at all. And so the plot on the left, you've compared the blue line to the green lines, is looking at the agreement of the observations with our model background, with the original height in blue, or if we reassign these low level ones to the cloud average pressure from the model background. And you see you get much better agreement when you swap to this using the information from the model to help decide at what height these winds are. And just in case you're thinking that there may be something slightly incestuous with that, we have looked separately at independent comparisons with independent data, radiosondes, and with AOLAS, the Doppler LiDAR in space, and that supports the change to the height assignment we're making. And when we do that, the plots on the right, just looking at errors in wind, latitude, pressure, cross sections at different height ranges, and the blues and green colours showing we are getting some improvement in the quality of the tropical winds from this change. And then finally, in terms of observations, there's a representativeness error added into the AOLAS total observation error. So big package of change on the observations and modelling side. And that then goes alongside a very, very major upgrade to the moist physics. So, of course, in the physics, we have boundary layer turbulence, representations of stratocumulus clouds, convection, shallow and deep. And this has been developed over many, many years at ECMWF, incrementally grown, improved, tuned, but it's become quite complex over the years. And so there's work here over several years to really try and improve the science, but at the same time clean things up, make it more consistent, better numerical representation. This has been a highly desirable thing to do. It's always challenging because the physics has been implicitly tuned over so many years. So when you give it a shake and start again, it requires a lot of work to recover the same performance. But as I'll show you, I think we've done better than recover the same performance. We have improved performance and a much, much more robust basis for taking the science forward now. So just in summary, it has a major impact on all aspects of the forecasts. As I'll show in more detail to come, there's many positives. Inevitably, with a physics change of such a pervasive nature, there's a few negatives. Separately from sort of quantitative scores, there's some changes to the character of cloud and precipitation, and I'll show some of this. I mean, it's probably particularly of relevance if you're interested in ECMWF products with a sort of forecaster viewpoint, looking at individual features and the characteristics of it. I'll show that tropical cyclone tracks are much improved and improved MJO. And as I said a minute ago, separately from the immediate improvements, the cleaning up, the tidying up of the code, the making the assumptions more consistent, makes this a much, much better baseline for going further forward, and in particular for moving to higher resolutions, looking at sort of order 3 to 5 kilometers in the future. So, how are we doing? Because this is a very, very busy slide, so don't worry that the slides will be available afterwards if people want to look in more details. But this is our highest level scorecard. So just to walk you around this, the left-hand scorecard there is for the high-res, the deterministic system. The right-hand one is the ensemble system. We have separate columns for scores for the Northern Hemisphere, the Southern Hemisphere, and the tropics. And then going down the page, we have different quantities, geopotential, temperature, winds, humidities. In the top half against analysis, and the bottom half against observations. And on all of this, blue is an improvement, red is a degradation. As I say, there's far too much to try and take in. The last thing I should say is in each horizontal bar, that's increasing forecast range. So the left end of each bar is day 1 and the right end is day 10. So just to try and walk you through some of the key things that we see in these scorecards. So first of all, looking at geopotential, so just highlighting the scores for geopotential on the left. And on the right, we have latitude pressure cross-sections of the change in high-res anomaly correlation. And so you can see we're getting quite noticeable improvements in the anomaly correlation. If you look at the Z500 time series in the bottom panels, you can see, depending on forecast range, we're getting improvements in anomaly correlation somewhere between 4% down to maybe 1% later in the forecast. So really quite a significant improvement in geopotential. Oops, sorry. So next one I wanted to highlight is the vector winds. So again, highlighted on the scorecards on the left in the black box, and you see very, very blue scores for the vector winds. If I look at the cross sections from the high res on the right, where blues and greens indicate an improvement. So in the extratropics, we've perhaps got 1 to 2% improvements in root mean square error. In the tropics, it gets up as far as sort of 7 or so %. The plots at the bottom are the tropics at 850 hectopascals and 500 hectopascals. So you can see, the first few days of the forecast, we've got improvements, root mean square error reduced by 5% or more. And as I'll show, the better tropical winds does translate to improved tropical cyclone tracks. Now, of course, I'm not trying to pretend that the scorecard is uniformly blue, so just to highlight some of the red features. So this is looking at the upper tropospheric temperatures, very much in the ensemble rather than in the high res. In high res, you don't particularly see reds here. It's quite strongly red in the ensemble. What's happening here, this is very much the result of a very small mean warming. So this cycle warms by a couple of tenths of Kelvin in the tropics. And the CRPS, because the initial bias is small and the CRPS is very sensitive to bias, that hits the CRPS score very strongly. If we actually look at a bias independent score, either the standard deviation of the error or a bias corrected CRPS, we actually have a positive or neutral change. So we've got just a small couple of tenths of a Kelvin increase in temperature is what's giving this effect. One of the challenges we face here is that the ensemble is just slightly warmer than the high res. Now that might be slightly counterintuitive, but it's an artifact of the current stochastic physics scheme where we perturb the tendencies from the parameterization schemes, with the result that the ensemble is slightly warmer than the high res, and so we can't actually get the mean temperature right for both of them at the same time. I think positively, we have a new stochastic physics scheme under development where it's SPP, where we perturb some of the physics schemes themselves rather than the output tendencies. And so we're optimistic of implementing that in a couple of cycles' time, and we'll sort of remove this dichotomy between the high-res performance and the ensemble performance. We look at sort of near-surface quantities. I think it's fair to say the signals are fairly mixed. If we focus down at the bottom, which is the verification against observations, to sort of really focus on the land results, and 2 meter temperatures, we see slight improvements in the ensemble verified against observations, 0.5% or so. The ensemble total precipitation is neutral to slightly improved. If we look at either of these against analysis, you get a less positive signal, which is very much restricted to subtle changes over the ocean. The difference between the analysis and the observations results is a land sea issue. The total cloud cover, we do see a slight degradation in the ensemble results. We have got a slight increase in cloud cover. There's about a 3% increase in total cloud cover, and that does give a slight degradation compared to SYNOP, and something we'll be looking at further in future cycles. So I'm now going to go on and look a bit more just at sort of separate from scores, just how some of the sort of the characteristics of the system change. I think particularly with a physics change, it's inevitable that just the way features look can be a bit different. So on cloud cover, I've already mentioned that the cloud cover is increased slightly. The other thing that changes is it's rather more binary. So we get less intermediate cloud covers forecast, and it's closer to 0 and 1. So this is just an example snapshot from a given forecast. The panel on the left is 47R1, which is the same as the operational high res effectively. And you see cloud cover, reds are the highest cloud covers, 1, down to the blues are just low amounts of cloud cover. If you look at 47R3 on the right, reassuringly, at a headline level, I think you would say that that's the same forecast. We're not expecting to dramatically change things. But of the area which is cloudy, rather more of it is red. So it's closer to we have no cloud, or we have almost complete cloud. So rather more smaller scale structure, slightly less smooth, which is a challenge for the scores. In terms of precipitation rates, there's also some subtle changes in the character of the precipitation. So this plot on the left is a single 30-hour forecast from the frontal system over France up to Denmark there, and it's just toggling alternately. Here's the new cycle, and then it toggles back to the old cycle. So the new cycle tends to have increased smaller scale structures, smaller, I think we believe more realistic rain areas, increased small scale structures, particularly in the convective rain over the sea, and slightly higher peak rates with more variability. It's obviously very hard to sort of, really in a quantified way sort of verify individual forecasts at this level. But I think all of these changes we're happy with, that they seem to be a step in the right direction. Another aspect of the model precipitation climate that we looked at is, of course, we run reforecasts in developing a new cycle. Many years of doing the reforecast to look at the model climate and how that's changed. So here we're looking at the 99th percentile of precipitation climate for the day 2 precipitation. So really just looking at the sort of the wet days, the 99th percentile, have we changed the climatology very much? And the answer by and large is we haven't. If you look across Central and Northern Europe, there's not very large changes in the wet end of the climatology at all. The exception is if we look a bit further south in the sort of semi-arid regions, Spain or into northern Africa, we do have rather more convective precipitation in these regions, and we're confident that's a good change. We've had some user feedback over the years that in these arid areas, on the rare occasions when it does rain, we're not raining enough, and so this change to sort of increase in the arid regions is a positive change. If we look more generally just at the distribution of precipitation, so this is looking on the left for the continental USA and on the right for tropical Africa, just looking at frequency distributions of precipitation. So if we look at the observations are in grey and black. If we look at blue, the control line, you'll see for both tropical Africa and the USA, at the left edge of the plot, the blue line is above the black and grey lines. So we have rather too much light rain. And if we look at the right end of the plot, the blue line is below the observations line, so we don't have enough heavy rain. And when we go to the 47R3 physics, we move to the red line, which is the angle is twisted, so it's much more close to the observations. So I think the new physics is better representing the observed PDF of accumulations. And I think that the last precipitation angle I wanted to look at, this is now looking at convective organisation, mesoscale convective systems over West Africa. So we have observations in the top left panel, and you can see an organised system propagating to the west. If you look in 47R1, the control forecast, it's much less structured and it's not propagating to the west. If it's propagating at all, it's arguably going east. And the 47R3 is the bottom left panel. And I'm certainly not trying to claim a perfect match, but I think you'd agree that sort of the characteristics of it, there's more structure, and with that more structure, there's more of a suggestion of a westward propagation. So certainly further to go in this very challenging area of modelling. It's challenging for all NWP systems, but I think a significant step forward. Moving on to tropical cyclone performance, I've already alluded to this. So the left box is looking at the track errors. So this is taking each ensemble member, looking at the track errors of each ensemble member separately, and then averaging those together. So error on the y-axis, time, length of forecast on the x-axis. The blue line is the 47R2 control, and the red line is 47R3, and you'll see that's below. The bottom panel is just bringing home the difference between those, so that the mean error normalized difference. And you can see for the first 5 or 6 days of the forecast, we're getting a 10% improvement in tracks with 47R3, the new physics. So that's a very pleasing result, a very significant improvement to the tropical cyclone tracks that we're very pleased with. Looking on the right, this is looking at the intensity errors. So this time from the high res. One characteristic feature we do get with the 47R3 physics is that the tropical cyclones are typically a little shallower. So perhaps 2 to 3 hectopascals shallower. And that across the mean is a small degradation, and it does give some increase in the mean absolute error. So we've got a significant improvement in the tracks, some degradation in the intensities, but even on the intensities, it's important to stress that these degradations are at the current resolutions, so 9 kilometers in the case of the high res. We've also done tests with the control physics and with the new physics at 4 kilometer resolution, which will be a future resolution of our system. And if we go to 4 kilometers, the new physics improves with a higher resolution. The intensities get better. The old physics, the control physics, the results actually degrade with increased resolution because the tropical cyclones get much too deep. So while we don't have an immediate intensity improvement here, I think we've put ourselves on a firmer footing for further improvements to come. Oops. Just a couple of case study examples, chosen just because I think they're broadly illustrative. So the top one is a recent Ida case. So there's a rapidly deepening tropical cyclone, and the black line is the observations, as circulated with best track. The blue line is what the operations did, and the red line is what the E-suite, the test of the new physics, did. And as I've just described, in this rapidly deepening case, we end up not quite so deep with the E-suite, which does verify less well. Although, as I've said, if we do the same experiment at 4-kilometre resolution, we're happier with the new physics. And even at present resolutions, if we look later in the life cycle of tropical cyclones, so in this case, tropical cyclone Larry, one effect we have at the moment is that the current physics tends to over-deepen. So this time, the black line is the observations, and the blue lines is what the current operations does. So later in the tropical cyclone life cycle, the current system tends to over-deepen, whereas the red lines are much closer to correct. Changing tack, looking at the extended range. So the plot on the right is our scorecard. I won't go into all the details of this, but our standard scorecard for the Madden-Julian oscillation. And we're getting significant improvements in skill of the MJO. We've also got an increase in MJO amplitude. So the MJO is better. Some of our early testing at lower resolution suggested that was translating into improvements in extratropical skill in the extended range. Perhaps disappointingly, we're not seeing that so strongly in the recent tests. So I would say the extended range forecast skill is, certainly the extratropics, is broadly neutral, but we have better tropics with a better MJO. Last thing I wanted to talk about was there's a range of revisions to products in 47R3. So first of all, visibility. So changes to the extinction coefficients in the visibility calculations. And I'm not going to go through these scatter plots in detail, but here we have observed on the y-axis versus forecast on the x-axis for fog on the left, rain in the middle, and snow on the right. The control in the top panels and the new 47R3 in the bottom panels. And on all of these we have improvements. Fog, previously the visibility was too low in thick fog. That's now improved. For rain, the visibility was previously too low in rain, is now improved. Snow, conversely, the visibility was previously too high and it's now reduced. So in all of these conditions, improvements to the visibility products. Also, a retuning of convective gusts. For some time, the wind gusts, which are effectively parameterized on top of the mean wind, there's a parameterization taking into account convection and boundary layer turbulence. In unstable conditions, for some time, we've had a tendency to, even if the mean winds were accurate, that the wind gusts were too strong. So here we've retuned some aspects of the gust parameterization, and across many cases that improves the statistics. So this is just a single case study, but I think it's fair and illustrative. If we look on the left, a single case study where we have observations, and you'll see we've maybe got sort of yellow and green colours over sort of northern France into Germany, which is sort of 26 meters a second. If you look at the operational forecast in the middle, we're getting into the orange colours, significantly overdoing it. The panel on the right, the 47R3, the colours much closer to matching the observations. So improvements to the wind gust products. There's a number of other products being introduced. I'm not going to go into the details of these. They're all available on the cycle page, more details of these. Just to mention that, in virtually all cases, they've been introduced in response to member state requests for different flavors of CAPE or neutral winds for wave modeling. So a variety of new parameters available. I'll just mention one or two now. So one is, for the first time, a clear air turbulence product, so based on the eddy dissipation rate. For any interested in the details, there's a tech memo and also a newsletter article which goes into this in more detail. Hopefully a useful product, and actually also for our further development work for the model, a useful diagnostic, because it gives us an extra way to assess the capabilities of the model. And then also CAPE, I mentioned there's various new CAPE parameters available. The current CAPE from the ECMWF system actually uses theta E in the calculation, purely for computational efficiency purposes in the diagnostic. The full parameterization uses theta V. What we're introducing here is a new, what's called most unstable CAPE that is using the full theta V calculation. So that's now available. So this MU CAPE comes out larger than CAPE. Interestingly, both are actually reduced by the 47R3 physics. So the new 47R3 MU CAPE will come out just slightly higher than the CAPE that users have been used to. But yeah, our recommendation would be that users use the mu CAPE. I think that's it's the most accurate calculation, and you find it typically similar to or just slightly higher than what's been previously available. So in terms of timeline and next steps, I'm not going to go into this in great detail because the information is all on the web page, and it's your best source of that data. But it's a bit of a landmark day tomorrow, the 14th of September, because that will be the start of the release candidate phase. And then, so really an encouragement to be using that, and then implementation coming on the 12th of October. So keep testing the data and software. Please do keep watching the information on the page to keep up to date with the latest news. It's users strongly encouraged to test their applications and data processing change. And we look forward to an implementation on the 12th of October. I think.